Okay, here is Peleus problem 12 from chapter 4. This is another one, I guess it ultimately boils down to a math problem, but what we're looking at is delta tau by L, the pulse spread per unit length, and we want to use equation 4.27 to show both of these approximations. Part A, delta tau by L is N1 approximately N1 delta over C, where here delta is the fractional index change, and I'll write down what that is. And part B, to show that delta tau by L is approximately equal to NA squared by 2CN1. Okay, and let me then just start by writing down equation 4.27, and that's giving the pulse spreading per unit length as N1 times the quantity N1 minus N2 all over CN2. Okay, and so we're going to start with this equation and derive the other two. Okay, so for part A, what we'll do is we'll start and we'll start by writing the definition for delta. This is the fractional index change and that's the delta that appears in part A's answer. Don't confuse this delta with the delta out in front of the tau by L. The delta out here just means it is a fractional increase in the pulse spreading per unit length. Okay, that's just the well, that's the notation the text uses, and that's the notation that we used in our development as I derived these equations in class. Okay, so don't confuse this fractional index change with the delta out in front here. That delta is part of the definition of this pulse spreading. Okay, so the fractional index change is N1 minus N2. N1's just slightly bigger than N2 usually, and so it's the fractional change as a fraction of N1. And so what we're going to do, the very first thing we're going to do is we're going to rewrite delta as, well, we've got a common denominator, and we're going to rewrite as 1 minus, see if I can erase this. Look at that. Nice. Okay, 1 minus N2 over N1, where I have N1 over N1 is 1. And so this gives us that N2 over N1 is 1 minus delta. And that implies further the N1 over N2 is 1 over 1 minus delta, but I can multiply that top and bottom by 1 plus delta, and that gives me 1 plus delta all over, and you see here the cross terms cancel. I get a 1 minus delta plus delta, they cancel, and then minus delta squared. And that's what we're always looking for here in these approximations, just like problem 4.8, where we can ignore the delta squared terms. And so this is approximately equal to 1 plus delta. Okay, so n1 over n2 is 1 plus delta. So now I can start, go back to equation 4.27, tau by L, and write this as let's see, I'm going to rewrite this, and I'm going to take this term n1 minus n2 and substitute for that delta times n1. You can see delta times n1 is n1 minus n2. So if this is delta times n1, I get delta times n1 squared in the numerator. So I get n1 over cn2 times n1 minus n2 delta n1. And so I get delta times n1 over c times, and then I'm going to take the other n1 from the numerator, put it here, and I'm going to put the n2 down here. So I've just rearranged the terms here. But now I have an n1 over n2, which I'm going to rewrite as 1 plus delta. So this is now approximately equal to, by the development above, delta times n1 all over c times 1 plus delta. But now when I multiply this out, I'm going to get a delta squared term in that second term. So this is approximately equal to, or it is equal to, delta n1 over c plus n1 over c delta squared. And here's where we make the approximation again. We ignore delta squared terms, and I get delta n1 over c. And that's part A. Part B now follows very quickly because we know from problem 4.8 that the numerical aperture, NA, is approximately equal to n1 times the square root of 2 delta. And so delta tau over L from part A is delta n1 over c. But n1, let's see, I'm going to substitute in for delta there, and I may run out of room. So it's n1 over c times delta. But from this thing, delta is na over n1 quantity squared, 1/2 of that. 1/2 of na over n1 quantity squared. And so now you can see the n1 cancels. So, I'm running out of room. Delta tau by L is na squared over 2c n1. And that does it. That's what we're after up here. So that's problem 4.12.